Bismillahirrahmanirrahim. Welcome to week 12 lecture, and this lecture is about. This is again from chapter on combinational logic. So until now we have been doing CMOS logic. So everything we discussed was CMOS, complementary metal oxide semiconductor logic, in which we have both NMOS and PMOS. Now this is not the only option to design circuits. There are other options, and in this lecture we are going to see some of the options that are used to design circuits not in CMOS. Now obviously the large percentage of circuits that you see in the real world are CMOS logic, but these logic families that we are going to discuss, they find some small applications for certain requirements. Okay, so let's see what are the logic families. So this is the outline of the presentation. Input order, asymmetric gates, symmetric gates, skewed gates, asymmetric skew, p-n ratio, pseudo NMOS, dynamic, and pass transistor logic. So let's discuss the input ordering first. So let's see what is the effect if one of the input is faster than the other. For example, imagine this scenario that we have A is 1 and B is 0 and then 1. Okay, so let's call this window of time t1 and this window of time t2. So A is always 1, B is 0 and then becomes 1. What will happen at the output of this gate? Remember, this is a 2-input NAND gate. Okay, so this is 2-input NAND gate. So whenever one of the input is 0 to a NAND gate, the output is 1. So in time period t1, the output is 1, and in the time period t2, when both the inputs become 1, the outputs becomes 0. So let's see what happens to the circuit in T1. Okay, so in T1, this is off, this is on, this is off, and this is on, which means that this PMOS would pull this output node to VDD. Okay, and this point X will be VDD minus VT, or it is approximately equal to VDD. The VDD minus VT is because of the drop across NMOS. Okay, so if we develop an Elmore model for this circuit, what will it look like? So first we have the output Y, to which we have connected capacitance of 6C. Then we have this point which is at VDD. Then we have an NMOS, and then we have another NMOS. This is the distance of this is r by 2, this is r by 2, so both should be connected in a manner that the total resistance is equal to the resistance of a unit inverter, which is R. So R by 2 plus R by 2 is R. And then we have at this point X, we have a capacitor which is 2C. Okay, so we calculated that this point is X is also at VDD minus VT. So the capacitor is also charged. So we can write the Elmore delay as R by 2 into 2C, which is this path, plus R by 2 plus R by 2. This is the resistance connected with 6C. So if we sum all this, we will get 7RC, and if we divide 7 by 3, okay, then we will get 2.33 tau. Now what is tau? Tau is basically the delay of an inverter, which is equal to 3RC. So we have represented the whole delay as in terms of inverter delay. So in this case, you see that if B arrives late, then we have the delay. So we have the delay equal to 2 point. For this one, we have the delay equal to 2.33 tau. Okay. Now let's consider the other scenario where A arrives late. So let me remove all this. So if A arrives late, that means that B is 1 and we have A which is 0, and then it becomes 1. So we have T1 time, T2 time, and again the output pattern will be like the previous one. So it is T1, it is T2. Now what happens in this case? This is on, this is off, this is off, this is on during time T1. Okay, so what that means is at this point we have a VDD voltage, but because this NMOS A is off, we have a 0 voltage here. Now if we draw the Elmore model, we have Y Then we have 6C here. We have this point at VDD. We have R by 2 and R by 2. Okay, and this we have a 0 volt here, and we have 2C here. Okay, now for this one, because there is a 0 voltage across 2C, so we don't need to consider this, because this will not discharge across R2. Okay, and we can write our Elmore delay as R by 2 plus R by 2 into 6C, which is 6RC. If we divide this by 3, we will get 2 tau. So for this one, it is 2 tau. Now, what this means is that a transition on A input, a transition on A input is faster. So one input is faster than the other one. Okay, so this is something that we have not considered until now, but this can be a problematic. One solution is that if you know the arrival times of your inputs, so you should connect the faster input to let's say faster inputs to B, so that the other one can catch up. Okay, so we have this definition of inner and outer outputs. So an inner inner and outer inputs. So an inner input is closer to output. So we say A is because A is closer to output, we say A is a inner input, and we say B is a outer input because it is near to the ground. Okay, so if the input arrival time is known, connect the latest arriving input to the inner terminal. So connect the one that is slower to the inner terminal. Okay, now let's come to asymmetric gates. So the next one is asymmetric gates. So asymmetric gates are gates where the sizes of NMOS and PMOS does not follow the 2:1 ratio. So where this can be helpful? This can be helpful when, for example, you know that input A for a NAND gate is critical. By critical, I mean that you cannot afford this to be slow. Okay, any transition on input, the gate should respond quickly. Okay, so one solution is to make the input A faster is to use smaller transistor on A. So a smaller transistor have less capacitance. Okay, and boost the size of non-critical input. So we have to do two things. We have to make the critical one small and the non-critical one large. In this way, the total resistance should be the same. For example, consider this NMOS, which has a size 4. So we know from the RC model that R by K is the resistance here, which means R by 4. Similarly, the resistance here is R by K, which means R by 4 by 3. So if you sum R by 4 by 3 plus R by 4, you will get R. So the total resistance is still the same as the resistance of a unit inverter. But if you calculate the logical effort for A, so the logical effort for A is 4 by 3 plus 2, okay, and this divided by 3, the capacitance of an inverter, so you get 10 by 9. And similarly for B input, which is reset here, so you have 4 plus 2 divided by 3, which is 2. So if you sum up these two, you get 28 by 29. Okay, so if you see that the critical input, which is A, the logical effort G approaches almost 1. So 10 by 9 is almost very near to 1. Okay, so which means that the gate will give a response that is quicker on A input. It is almost as quick as an inverter, because an inverter has a G equal to 1. But on the other side, the total logical effort goes up, because we have made A faster, but the B input has become slower. So the logical effort has gone up. So these are asymmetric gates. So asymmetric gates can be used when you know that one of your input is very critical, and you have to be very fast in order to produce its output. Then you can use asymmetric gates. Now if we want to make a symmetric gate, a symmetric gate has the property that it does not favor any input. What this means is that it processes both the input in a similar fashion. And how that is developed is that the NMOS stack is replicated twice, okay, and then the A is connected once at the bottom. So once it is connected at the top, it is here, and once it is connected at the bottom. Similarly, B is once connected at the bottom, and once it is connected at the top. By top I means near to the output. So we have seen that the inner inputs are the one which are near to outputs. Okay, inner inputs are faster. So the symmetric gates connects both the inputs in such a way that in one stack, one is the inner input, and in the another stack, the other is the inner input. So this kind of symmetry makes the gate process both A and B simultaneously in a similar fashion. So there is no difference in timing. So if you want, you can develop symmetric gates. Obviously, you have to use, let's say, more transistors, so the area increases, the power consumption increases, but you have perfectly similar timing for both the inputs. Now skewed gates. So skewed gates favor one edge. So this is the important word. It favors one edge over another. Suppose the rising output of an inverter is critical. So you can use a skewed gate for that. So what the skew gate does is downsize the non-critical NMOS. So you have this requirement that you have an inverter for which the rising this edge, this is critical, so it should be reduced in least amount of time, as quickly as possible. So what that means is, like, for example, this is the ideal one. So if it is slow, it will be like this, but if it is fast, it will be like this. So it has this RC charging time is what makes the transition faster and slower. Okay, so the method is downsize the non-critical NMOS. So if you want to have a fast rising time, so you have to downsize the non-critical NMOS. So you make an NMOS 1/2, half the size, and the PMOS stays the same. So this is this one is the original one, which is unskewed, and this is the called high skew inverter, in which the NMOS is half the size of a normal inverter. Okay, now to calculate the logical effort, we can say that it is 2 plus 1/2, which is 2.5, divided by 3, which is 5/6. So this is the logical effort of up transition. Okay, so 0 to 1 transition. What is the logical effort for down transition or 1 to 0 transition? For that, what you have to do, you have to follow this process, that the NMOS will remain the same size, but the PMOS will become half the size. Okay, and then you add up, then what you do, you compare this one with this one. Okay, so this is your comparison. You don't compare with the normal inverter, but you compare with an inverter that has equal fall resistance. Okay, so for that case, the A is 2.5, and then note this is not 3, which is for a normal inverter, but this is 1.5, which comes from here. So you have the down logical effort of 5/3. So this is the definition of high and low skew. Okay, so logical effort is, you can read this definition. So skewed gate reduces the size of non-critical transistors. High skew gate favors rising output. This is the definition of high skew. Low skew gates favor the falling output, and this is how you do it. Make the NMOS smaller for high skew, make the PMOS smaller for low skew. Logical effort is smaller for the favored direction. So whichever direction you want to favor, the logical effort will be less for that, but larger for the other direction. So for example, the logical effort is smaller in the favored direction, so which is the up transition, and it is larger in the other direction, which is down transition. Okay, so here is a catalog. So let's discuss some of these gates and how we calculate the logical effort. So consider the two input NAND gate. How can we size this NAND gate? So we have a PMOS of size 2 2, and this is our non-critical input, so we reduce its size from 2 to 1. Okay, so this is a skewed gate now, and we can calculate the logical effort for 0 to 1 transition or up transition is 3. So if we look into A, we see 1 here and we see 2 here, so it is 3 by 3, which is 1. So this is for the up transition. For the down transition, we have again resistance, input of 3, but this time we don't divide by the capacitance of a normal transistor, a normal inverter, but we divide it with the capacitance of half the inverter. Okay, so we already discussed this in the previous slide, that we will use this inverter where this size is 1 and this size is PMOS size is 1 and NMOS size is half. So the overall capacitance Cn of this is 1.5. So we will always divide with 1.5 for the down transition, which gives us 2. We can then take the average of these 2. So which is 1 plus 2 divided by 1 plus 2 divided by 2, so it is 3 by 2. Okay, if we consider the 2 input NOR gate, so the size of PMOS will be normal, but the size of NMOS will be half, because this is the non-critical input. So we can say the logical effort for the up transition is 4.5 divided by the capacitance of a normal inverter, and this is 4.5 divided by the capacitance of a half size inverter. So this is 1.5 and this is 3. Okay, so then you can add these up together, 1.5 plus 3 divided by 2. Okay, so this is how you calculate. I hope that you can calculate for the other ones. For the low skew ones, you have to do it yourself. Okay, then we come to asymmetric skew. So what is asymmetric skew? Combine asymmetric and skewed gates. So it is basically the combination of the two previous discussed methods. So we have to downsize the non-critical transistor on unimportant input, and we have to reduce the parasitic delay. So if we do both of these, then the gate is called asymmetric skew gate. For example, consider this one. We have the size reduced, okay, and then we have the capacitance reduced. Okay, so the PMOS is not 2 but it is 1. So this kind of gate is called asymmetric gates, asymmetric skewed gates. Okay, then what is the best P and N ratio? By P and N ratio, we means the size of PMOS versus the size of NMOS. So until now, we have been using 2:1. Okay, but you can change and you can play with the P to N ratio. Okay, and this affects the delay and everything. So imagine that you have an inverter which instead of here 2 you have a P which is a variable. Then you can play around with this, and then this is some derivation, and it shows that the least delay for is when you have a square root of u, where u for an inverter is mobility, and it is in the range of 2 to 3. Okay, so in general, this P/N ratio is the square root of equal delay ratio. So for example, if you consider this one, it is basically under root 2. So before it was 2, now it is under root 2. So you should go in if you want to reduce, if you want to play with the P and N ratios, it's better to go as a square root of the sizes. Okay, so now if you calculate the GU, it is this, GD is this, and G average is this, which is quite near to a unit inverter, but the size of this inverter is less than the size of a inverter which has a 2:1. So if you consider this one, it has a 2:1. So this takes more area compared to this one, but its logical effort is almost close to the normal one, and it favors the up transition compared to the down transition. So you can go like that and calculate the average logical effort for these gates, which you know very well. So this is P and N ratio. So observation is NAND for speed, NAND versus NOR. So which one is faster? NANDs are faster because PMOSs are slower, and in an NOR gate, PMOSs are in series. So where we have PMOSs in series, it will be slow. So that's why in CMOS logic, a NAND is better than a NOR. Okay, and so for speed, do NAND, use simple stages having high fan-in stages, latest arriving inputs. For area and power, many simple stages and high fan-in stages. So these are just some observation that if you want to optimize area, what should you do, and if you want to optimize speed, what should you do. Then let's move on to some other circuit families. But before moving on, let's consider what makes the circuit fast. So we have, for a capacitor, we have I is equal to C dV by dt, and if you rearrange for delta t, it is proportional to C by I into delta V. So what this formula says is, if you have a low capacitance, you will have a higher speed. If you have a high current, you will have a higher speed. If you have a small swing in your voltage, you will have a higher speed. So all these three facts are coming from this formula. Okay, So the logical effort is proportional basically to the ratio of capacitance by current. And I already told you that PMOS are not good, because for the same current which passes in the gates in both PMOS and NMOS, the size of PMOS is greater. For example, consider this one. You see, this is a NOR gate, 2 input NOR gate. You see, for the same current flowing through the circuit, the size of PMOS is 4 times the size of NMOS. So this is huge, and this affects also the propagation delay, TPD, because a higher capacitance means that it will take more time to charge. So one very basic principle that is used by all the logic families that are in the upcoming slides, they exploit this fact that PMOS are our enemy and we should remove them from the input path. Okay, so various families try to remove the PMOS because they are slower than the NMOS. So the first family that does this is called pseudo NMOS. Why it is called pseudo NMOS? Because before CMOS was commercialized or discovered, you can say, okay, before CMOS there was only NMOS logic. Okay, so the industry used only NMOS to build circuits because they didn't know how to combine NMOS and PMOS on a single substrate. The construction of NMOS and PMOS uses different kinds of gate materials and everything, so they didn't know how to combine the NMOS with PMOS. So this was before CMOS, so everything was in NMOS, so those circuits were faster. But if you want to create the same effect, then you can use sort of pseudo or false NMOS. For example, this is a pseudo NMOS inverter in which the PMOS is always connected to ground. What this means is that the PMOS is always on. Okay, so if this is an inverter, so imagine this is an inverter in which the output is by default 1, and then depending on the input, if the input Vn is 0, okay, then the output stays 1. But if the input Vn is 1, this transistors the NMOS turns on and it pulls down the V out. It pulls down the V out towards ground. Now there is a sort of fight between PMOS, which tries to pull up it to VDD, and between NMOS, which tries to pull it down to ground. Okay, so that's why in order for the NOT gate to work, the PMOS used is a weak PMOS, so it is not a strong PMOS. Okay, and how we can achieve it is by sizing the PMOS. So you see on the right we have the characteristic curve of NOT gate. On the x-axis we have Vn, on the y-axis we have Vout, and then we have these curves for different P sizes. For example, for P is equal to 4 we have this curve. okay, which says when p is equal to 4, the size of PMOS is 2 and the size of NMOS is 8. So you see the larger size of NMOS means that it will have a higher current carrying capacity. Okay, it is stronger. So compared to PMOS, the NMOS is very strong here. Okay, and by default the output is 1, but when the Vn turns 1, so this is, for example, above 0.9 is our 1 on the input side, the output drops to 0. You see, it is not exactly 0. See, it is going here compared to a normal inverter where it will come to 0. This does not come to 0 because of the pull up effort by the PMOS. Okay, so this is pseudo NMOS, and in pseudo NMOS you have always this PMOS that pulls up to ground, and in this way you don't need the PMOS in the not in the input path. So this PMOS is not in the input path. Okay, it has no relationship with the input. And if you sort of calculate the logical effort of this one, which has PMOS has a size of 2/3, NMOS has a size of 4/3. So you see that the logical effort for up is only a function of the A input, which is connected here. Okay. So for the inverter, given here, we see that our input is connected to the NMOS, which is a pull down transistor. So if we consider the pull down phase, the current that is flowing in the transistor is proportional to its width. So it is 4/3I, but at the same time the PMOS is always on and it is pulling it up, and it is pulling it with 1/3 strength. So if you consider this, it will be I. So you say that for this, if we consider the unit inverter, so a unit inverter has a current I flowing, and same current is flowing here for these dimensions. Now see that I have left out the 2 for the PMOS because it has always a ratio of 2 with NMOS, and this is when you compare it to the normal inverter. So we are comparing it to a normal inverter. So that means if we want to calculate GT, which is the effort when you are pulling down the transistor, it will be equal to the capacitance, which is 4/3 divided by the capacitance of a unit inverter. So you multiply it with this, which you get 4/9. So this is when you are pulling down the output. When you are pulling in the pull up, the current is 1 by 3 of the current flowing here, so we just multiply the logical effort of 4 by 9 into 3, so we get 4 by 3. So this is from where 4 by 3 is coming. Because our input is not directly connected to the pull up, we calculate it indirectly. We first calculate the pull down, and then from that the current is 1 by 3 times of that, so the capacitance is inversely proportional to the current, so we multiply it with 3. So for the average, we just add these up and divide by 2, so we get 8 by 9. Similarly, for the parasitic delay, we first calculate PD, which is 4 by 3 plus 2 by 3. So these are the two capacitances that are connected to the output, which is 6 by 3. Okay, and we divide this by 3, so we get 6 by 9, because we have to compare it with a unit inverter. Okay, so this is 6 by 9, and for PU the propagation the parasitic delay is 6 by 9 times 3, so it is 6 by 3, and then you just average it out. Similarly, if we consider, for example, the NOR gate, we first calculate this one, which is our downstake. It is equal to 4 by 3 multiplied by 1 by 3, which is our effort of normal inverter. So it is 4 by 9, and in this one, this the downwards we multiply it by 3 because of this factor. Similarly goes, we first calculate PT and then we calculate PU. Okay, so this is how you calculate the logical effort and everything for pseudo NMOS. Now if you compare this with CMOS, okay, so pseudo NMOS is faster. Pseudo NMOS is faster compared to CMOS. If you compare all the logical efforts and parasitic delay, you will see that the NMOS, pseudo NMOS logic is fast, but let's consider its power consumption. So the pseudo NMOS draws power even when output is 0, because of the PMOS that is connected, that is always on. So it has a static power consumption. So it is equal to IDD into VDD. Although that the current is only a few milliampere, but this is per gate. So if you have 1 million gates, then it will be considerable amount of static current, and this explains the reason why pseudo NMOS went extinct. So it has a huge static power consumption. But pseudo NMOS is used for designing NOR gates, because in the previous slides we have seen that the logical effort for a NOR gate on the average was 8 by 9, and it's independent of the number of inputs, independent of number of inputs. so it doesn't increase with the number of inputs. So if you want to design higher input NOR gates, pseudo NMOS logic will be a lot faster than CMOS logic. Okay, one way to reduce the static power consumption is to use the enable logic. So remember that before, the PMOS was connected to ground and it was always on, but you can connect it to a user signal enable, which is controlled by the user, and in this way you can reduce the static power consumption. So let's consider this example. A chip contains 32 words multiplied by 48-bit ROM. So you have a ROM which has word 0, word 1, word 31, and each of the word is 48 bits. Okay, use a pseudo NMOS decoder. So you already know that we always use decoder. So we will use a decoder here, which will be a 5x32 decoder. So it will be connected to the enable logic of each word, and on the average one word line has 24 bits are high. So if you consider that here you have each one has 48 bits, so each one has 48 bits, so it says that on the average for 24 of these bits are high. Find the static power consumption of the ROM when the on current is 36 microampere and the supply voltage is 1 volt. So in the pull up transistor, where PMOS is always on, VDD into I pull up is 36 microwatt. It is the total pull up power consumption. So if we want to now calculate the static power consumption, it is basically that at any moment only one of the word line is selected, which means it is high, and 31 are low. Okay, so we have 31 lines which are low, which means they will consume the static power consumption. They should be off, but because of the PMOS pull up, they will consume the power, they will have current, and in each of these 32 lines there are on the average 24 bits that are low. So this is the percentage of 36 microwatt that results in the static power consumption. So it is equal to 1.9 milliwatt. So 1.9 milliwatt only for a ROM. So it is a huge power consumption. So the pseudo NMOS is better for wide input NOR gates, but we have to remember that the power consumption is huge. Now let's move on to another logic family, which is called dynamic logic. Dynamic gates use clock. Okay, consider this as our static inverter, and this is our pseudo NMOS inverter, in which we have a ground connected to the PMOS. In the dynamic logic, we have this phi, which is our clock, and the phi is given here. So you have a 0, 1, 0 cycle. The 0 is called cycle is called pre-charge. So when this is 0, the PMOS is on and the output is pre-charged to VDD. So you see that the output is VDD, and when the clock is 1, this is called evaluate phase, and now it depends on the input A. If the input A is 1, when the clock is 1, then the output will be pulled down from its pre-charge value to the ground. Okay, and in this way it continues. So you see that the inputs are only evaluated in clock is equal to 1 phase. Okay, but there can be a problem. What if the pull down network is on during pre-charge? So if your NMOS is on during pre-charge, then it will be the output will not charge up to VDD. It will be dissipated across the NMOS to the ground. And why would that happen? Because you cannot constrain the user. So the input A is coming from the user. So either you have to tell the user that you can only pull down the network during evaluate, and you cannot pull down it in pre-charge. If the user abides by this discipline, then it's okay. Otherwise, we have a problem. In order to solve that problem, we add another NMOS that we called the foot, and this NMOS is connected to the clock. So we have two kinds of dynamic logic. One is called footed. So we have the PMOS here, we have our function here, and we have our foot here, and then we have the unfooted. Okay, so if you want that the pull down network should not discharge your output line during pre-charge, you should always use the footed logic. So again, we can calculate the logical effort of dynamic logic. So we have for this one 1 and 1 as our K value. So the input capacitance is 1 divided by the input capacitance of inverter, which is 3. So we have 1 by 3. The parasitic delay, because we have two capacitances connected to the output line, so 1 plus 1, 2 divided by 3. Similarly, if we go to the footed one, then the footed one gives us the the logical effort as 2 by 3 for the down transition, and the parasitic delay at this point we have 1 plus 2, 3 by 3. Okay, same goes for the 2 input NAND gate. The GD is this one, 2 by 3, and the output is 3 by 3. Same goes for a 3 input, a footed one. So in a footed one we have 3 by 3, and we have 4 by 3. So you can do the others. Okay. Now there are certain problems with the dynamic logic. One is that the dynamic logic requires what is called monotonicity. Okay, so what that means is that during evaluation you can have a 0 to 0 transition, 0 to 1 transition, 1 to 1 transition, but you cannot have a 1 to 0 transition. This is not allowed. Let's understand this with this timing graph. So this is our clock. We have pre-charge, we have evaluate, we have another pre-charge. So imagine during pre-charge your output is 1. Okay, this is a footed NOT gate. During evaluate, when you look to your input here, it is 1. So when it is 1, your network should pull down. Okay, so the output becomes 1, but at this point your input again becomes 0. Okay, so when that becomes 0, the output should rise like this one. Okay, output should rise to the VDD line, but it cannot rise to VDD line because it is only done in the pre-charge stage. So this change of 1 to 0 is not allowed. What that means is during the evaluate phase you cannot change your input from 1 to 0. Okay, so this is as requirement which is called monotonicity. Now this is aggravated by another scenario. So if you have two inverters, two footed inverters, what can happen at the node X, that the node X can be driven from 1 to 0, which is not allowed. So again, because of the monotonicity requirement, your input A is always 1, but your X goes from 1 to 0 during the evaluate stage, which is not allowed. Okay, and that's why your output should be this one, but it is actually this one. Okay, this is because of the monotonicity requirements. So what that means is that dynamic logic cannot be used until monotonicity is satisfied. How can we satisfy monotonicity? It is done by introducing a NOT gate between the dynamic stages. So imagine if this is dynamic NAND gate and this is another dynamic NAND gate, you should always introduce a CMOS static inverter. So every stage of a dynamic NAND should be followed by a CMOS NOT. So this is, you see, this is dynamic NAND, this is CMOS NOT, this is dynamic NAND, you see this clock symbol, and this is CMOS NOT. So when you do like this, the timings and the monotonicity requirements will always be fulfilled. Okay, if you want to understand this, go through this timing diagram and you will understand that the monotonicity requirement is now satisfied in this fashion. So this is called Domenio logic or Domenio gates, dynamic or Domenio gates. Okay, so here is a circuit for 8 cross 1 mux that is made up of this is 4 cross 1 mux domino, okay, and this is another 4 cross 1 mux, which is domino logic, and these two are connected with a high skewed static gate. Okay, so you see here we have the clock, here no clock. Okay, we have no clock. So why high skewed? Because we want that the transition from 0 to 1 should be very fast. Okay, so domino, why it's called domino logic? Because it's like a string of domino toppling over. So remember that you have like these dominoes, and if one of these topples, it triggers a chain of toppling of dominoes. So gates evaluate sequentially but pre-charge in parallel. What that means is that if you have for example this as a domino gate, then you have a static gate, then you have another domino gate, then you have a static gate. So what will happen, that first it has to trigger, okay, it has to compute, then the next one, so this is 1, this is 2 cannot trigger until 1 triggers. Okay, so and all of this triggering should happen in evaluate phase. Okay, so it means that the speed of this computation, which is happening sequentially, is very critical. Okay, so evaluation is very critical for the speed than the pre-charge. In the pre-charge state, all the domino gates will charge to a high value simultaneously in parallel. Okay, so let's come to dual rail domino. So domino only performs non-inverting functions. Because of the monotonicity requirements, we can have only AND and we can have OR, but we cannot have NAND, NOR or XOR directly. This is solved by what is called dual rail domino logic. It takes both true and complementary inputs and produces true and complementary outputs. So we have something like this. So you have F bar and you have F, and they are connected with the same clock. You have the same foot, and on one side we have Y low and the other side we have Y high. So for example, if this is the function, here is the true version and here is the complementary version. Okay, so let's see an AND and NAND/NAND gate to understand it better. So you see here we have the complementary side, so Y low, and here we have the high side. So on the here on this side we have a AND gate, and on this side we have a NAND gate, and both are connected to the same PMOS, to the same clock. Okay, they are connected to the same clock. And then we have for NAND this parallel combination, and for AND we have this series combination. Okay, why this for NAND? Because a NAND gate is like this, so we can implement it as A bar plus B bar, and that is what is meant by A low. So it is A low plus B low. Okay, so they are connected in parallel, which is basically a NAND gate. If you have a NAND gate, it is equivalent to this OR gate with bubbles. Okay, so we have this kind of implementation. So in this way you can have both AND and NAND implemented in the same gate. So this is called dual rail Domino logic. Sometimes it's possible to share the transistors. So for example, if you can, this is one implementation of XOR and XNOR gates, and you can go through the details of how it is XNOR and this is XOR. You have to start with the basic equation. So I think for XNOR it is something like A bar B bar plus AB bar AB, I think. So it is 1 when both are 0 and when both are 1, so when they are same. So if we look to this side, it should implement this equation. Okay, and you see that there is a sharing. So this transistor goes to here, this transistor goes here. So let's check it for A is equal to 0 and B is equal to 0 to see if the XNOR is 1 or not. So when A is equal to 0, this is 1, this is 1, this is 0, this is 0. Okay, so we are just looking to the left side, and this is 1 because we are in the evaluate phase. This is 1, so this point is at ground, so this point is at ground, and this is 0, so this transistor is off, and we have a static inverter here, so it will be 1. Okay, so the XNOR value is 1. Similarly, you can check for other combination to be sure that this is a XOR and XNOR gate. There are some other issues with the Domino logic. So dynamic node floats high during the evaluation phase. So during the evaluation phase, when we have the phi is equal to 1, the transistors, the PMOS should be off, but because of leakage, I off is not equal to 0, and the dynamic value will leak away over time. So your output needs to be at a certain value, but because it leaks away, it can be changed. So what is the solution? We use keepers to hold the dynamic node, but you should remember that the weaker must be weak enough not to fight evaluation. What that means is this thing, that we insert this blue weak keeper, which is in feedback which is in feedback with the output. So what happens when you have the clock equal to if this node is, let's say if this node is 1, or let's say if clock is 0, okay, so this PMOS will be on and this will be connected here. So you will have a 1 here, and this is inverter. You will have a 0 here, and this 0 goes here, so you will have again another 1 here. So when you are in the pre-charge state, the feedback loops keep y keeps y at sorry. Okay, so you see during the when we have this, then we have a feedback loop which keeps node x at 1. So this is the output of Domino NOT gate. So when we have the pre-charge stage, x is always at 1 due to this feedback. But when we have evaluation stage, and imagine that A has not arrived, then in the evaluation stage, the this PMOS, this should be off, but this is not off because of the leakage, and in this way your node X can discharge across the NMOS. Okay, but due to this feedback arrangement, your output node X will always stay at 1 at VDD until A arrives. Okay, then there is another problem that we have to consider in domain. Now consider this scenario that when the clock goes to evaluate phase, so you have already pre-charge the node Y to VDD in the pre-charge stage, and during the evaluation the A goes from 0 to 1. So that means that this transistor NMOS is turned on, and we have a path between these two capacitors CY and CX. Now what will happen, that the output capacitor will start to discharge, and the CX capacitor will charge to certain values, and that certain values is when both the voltage at both the node X and Y becomes 0. Voltage at Vx and Vy becomes equal. Okay, until that time one capacitor will discharge and the other capacitor will charge. Okay, note that B is always held to 0 in this configuration. Now this should not happen, because in domain logic you want that your node should be kept at the voltage VDD, and it should only be brought down when the logic requires. So in this scenario the pull down stack is inactive,
So we are not pulling down the output to ground, okay, because this is off, but our capacitors are discharging, and this discharge can effectively bring the voltage on the output capacitor to a level that it becomes logic 0. So that will be wrong. Okay, how we can solve this problem? We need to keep the node voltage at node Y equal to VDD, and we also need to keep the voltage at node X to equal to VDD. So this internal node also needed to be pre-charged. So for that we have to add the second pre-charge transistor, which will keep this internal node X at the voltage VDD. Okay, so typically if your gate number of inputs to the gate increases, then you need to pre-charge every other node. So not every node, but every other node. Okay, other solution is to connect your output CY to a very big load or capacitance, but this is not a general solution, because it depends on what you connect your output to. So you cannot design your gates like that. You have to correct it internally, not according to the load that is connected. Now another disadvantage of domino gates is that they are very sensitive to noise. Remember the CMOS property that CMOS are restoring. So this is a very beautiful property of CMOS that enables it to cascade multiple levels of gates. But domino logic has no restoring properties, and if there is an input noise at the input, or even noise at the output because of the feedback of the weak keepers, then the domino gates will sort of amplify it as we go from one domino gate to the next domino gate. And there are several sources of noises in digital circuits. So we have capacitive crosstalk that can happen between two wires carrying current. So if they are very close to each other, they will have a crosstalk or noise. We have seen that there is a problem of charge sharing in the previous slide. Then we can have power supply noise, we have feedback noise, and there are so many other sources of noise. So domino logic is very susceptible to noise, and that is quite bad for the reliability of circuits. Another drawback is because each domino logic, for example, this is a domino AND gate, and we have this clock. So because of the clock, there are so many transitions happening every time. This is unlike a static CMOS gate, which does not have the clock. So whenever you have the clock, you have a lot of data transitions that are happening due to the 0 to 1 flipping of clock. So this leads to a very high power consumption. So domino logic is also limited by the power consumption, and as you know that power consumption is becoming a huge issue. So this is the summary of domino logic. It is very attractive for a high-speed circuit. It is at least 1.3 to 2 times faster than CMOS, but there are so many challenges. You have the challenges of monotonicity, we have the challenge of leakage, we have the challenge of charge sharing and noise. So mostly domino logic was used in 1990s when we have a uni processor, and the industries used to increase the speed of uni processor with every new iteration. So Intel logic was used in 1990s, but it is being slowly replaced, and it is out of use because of the power consumption issue. Okay, maybe in memories there may be some usage in memories even today, but that is a very small small domain in which they are used. Okay, so the final logic family is pass transistor. We have already covered this in chapter number 1, so I will quickly go over this. So you can use pass transistor like switches to do logic, and inputs drive diffusion terminals. So inputs can be connected to here, for example, to the source and drain, not only gates. So you can build from CMOS logic, you can build transmission gates, and here is a circuit of 2x1 mux. It uses two transmission gates, and we have already discussed this circuit, but we know that the pass transistor logic is non-restoring. One way that we can restore it is to use, for example, CMOS inverter or buffer, whatever you have, to restore the logic. Okay, then we have another modification which is called leap or lean integration with pass transistors. So basically it get rid of the PMOS transistor. So this is again 2x1 mux. It uses half the transistors of a pass transistor logic or transmission gates. It has only NMOS, and we know that the NMOS passes a weak 1. So this is the solution to restore 1 fully. And how it restores it, that whenever this node, call it X, is 1, this output is 0 and this is 0. So this VDD is connected to this point, so it basically pulls up the point X to VDD. Okay, but when you have 0 here, then you have 1 here and you have 1 here, and this PMOS is off, so it doesn't have any effect on the value of 0 at node X, but the value at 1, the value of 1 at node X, it pulls it up to the VDD completely. Okay, so remember that when your 1 passes, so for example if A is 1, so 1 passes here, it will be VDD minus VT, but due to this feedback, okay, this will be pulled completely, not to VDD minus VT, but to completely to VDD. Okay, so this is the function of this weak PMOS feedback loop, and it should be ratioed. So what this means, that NMOS should be stronger and PMOS should be weaker. So it should have a higher width, NMOS should have a higher width, so to deliver higher current than the PMOS. and then I will just go over this. So complementary pass transistor logic, it is like the dual rail domino logic, and it uses two copies, and we have the complemented and uncomplemented outputs. Okay, so this is the summary. Pass transistor logic is not very interesting. It is proven by researcher. It has very small or negative benefits over static CMOS, but it can be used in a very small fraction of circuit, particularly for memory, because they offer small size, and the threshold drops in memories can be managed. So this is the end of lecture number 12. We have discussed several logic families, and gave you a flavor of how we can calculate the logical effort and parasitic delay of some of these circuit families. So this is the end of chapter number 9, I think, which is on the combinational logic, and we will continue with sequential logic in upcoming week.